Wonderful. Thank you. Hello, my name is Bhatt. I'm a second-year bioengineer, and today I'd like to present to you Vasudhara 1, a bioreactor designed for improving the accessibility of bioprocessing. Now, the first question is, what is a bioreactor? A bioreactor is a device that cultures and grows cells using either human microbial for use either in chemical processes or for growth chambers. And this technology can be used to obtain valuable and complex compounds at a fraction of the cost. A great example of this is alcohol. If you were to synthetically make alcohol, you could, but the cost would be high, the yield would be low. Instead, you could employ yeast and a bioreactor to produce alcohol and simply purify the product. And this type of workflow is why bioreactors are used in a variety of fields. This includes industrial biotechnology and bioprocessing, of which these fields are responsible for the COVID vaccines, as well as waste treatment, where bioreactors are used to break down organic waste into smaller compounds, and brewing and food production, as well as many other fields. So with all these uses, it's important to state that bioreactors are an incredibly important tool for bioengineer and chemical engineers' toolbox. And by having access to these tools, these undergraduates can not only learn the technical skills and operations skills necessary, but can also be more competitive in the workforce. Despite this, bioreactors are incredibly expensive. And during a regular year, having access to a bioreactor as an undergraduate is difficult. But during the last year, during which the pandemic forced the campus to close, it was near impossible. So as a second-year bioengineer, and perhaps the most ripe time of my undergraduate degree, how would I have access to this incredible tool? Well, it's simple. I'd make my own. And here's why I introduced Vasudhara 1. Vasudhara is the name of the Buddhist deity of abundance in reference to how a bioreactor grows many organisms from a single starter culture. It is a simple photobioreactor, photo meaning light, and uses light to culture algae. I built this in my room using a large fermentation jar, common electronics, and an Arduino microcontroller. Additionally, I sadly had no funding for this project. So let's first talk about the culture. On the rightmost here, you can see green spirulina, which is a very economic microorganism used in a variety of fields. It's commonly grown for food, supplements, cosmetics, and research, and is being looked at for its potential as an anti-cancer treatment. As you can see in this green image there, that's what the culture looks like at the ripe of its growth, where the bubbles show that the algae is photosynthesizing in this culture flask. Now, in order to create a bioreactor, I had to have several modules attached, and these modules carried out a specific function. The first function I had is a display and temperature module. Here I used a stock LCD screen that comes with most, if not all, Arduino kits, and a MAX 6675 thermocouple, which is a digital thermometer. The function is simple. It's to obtain and display the temperature data. And as you can see by the image, it does just that. Now, this is the Arduino code. And while this does look complicated, most of this is just setup code. In fact, the only important line is the LCD print thermocouple line, which simply takes the data from the thermocouple and displays it on the LCD screen. Having this information displayed is incredibly important, as it allows the operator, in this case me, to move the bioreactor in and out of sunlight or towards cooler or warmer areas, best suited for the growth of the microorganism. Next, I added an agitator. Now, an agitator is also an incredibly important part for any bioreactor, as it allows gas exchange as well as the distribution of nutrients in the media. As you recall from high school biology, animal cells take in glucose and oxygen and produce carbon dioxide and water. This carbon dioxide in large amounts is toxic. Alternatively, for plants, having too much oxygen in the water is also toxic. So by having an agitator, you not only promote gas exchange, but you can also distribute the nutrients. And for photobioreactors at large cell densities, this is important so that every cell can have access to light. Now, I made this using a stock 5-volt DC motor, which comes with most, if not all, Arduino kits, a 3D printed impeller, an impeller being the opposite of a propeller, which instead pulls up water instead of pushes it. And this was a conscious design choice, as it allowed me to have the agitator not draw out as much current, while also maintaining the other systems. Additionally, this comes with a stock Arduino joystick, as you can see in the image, and an L298 motor controller, which I used to program and control the motor. Here on the left is the image of the agitator, which I modeled in Tinkercad, a free online 3D modeling software, and in the Arduino code. The code, despite looking complex, is also simple. It simply takes the positional data of the joystick and corresponds that to a certain output, and uses that output to determine the direction and power of the motor. This allows me to have control over how much current is drawn using the motor, and thus not short out or depower the other systems on the Arduino. Now, the next component I made is the spectrophotometer. But before I go into how I made it, it's first important to understand what the spectrophotometer is and the significance of this project. A spectrophotometer is a device that's used to obtain the absorbance of a solution by passing light through a sample. A great example of this is coffee. For example, if I give you a strong cup of coffee, you could see it's very dark and less light would pass through. Alternatively, if I gave you a diluted cup of coffee, you could see that it's lighter in color and then more light could pass through. This is what a spectrophotometer does, and that value is also called absorbance. Now, the reason I also made a spectrophotometer is because spectrophotometers cost upwards of several $1,000s. So by having this tool as well, I not only save money, but also gain the functionality of an incredibly important piece of laboratory equipment. Here I go more in detail on what I do with the absorbance value. Since absorbance is a measure of how much light passes through a solution, I can use the Beer-Lambert's law and correlate this to concentration. Going back to the coffee example, the strong cup of black coffee just had more stuff in there. Alternatively, the lighter cup of coffee had less stuff in there compared to its total volume. Using this, I could then derive some idea of what the cell density of the solution was, and therefore a rough approximation of how many organisms were also in the solution. A careful design note is that when I made the spectrophotometer, I had to use a light opposite to the color I perceived it as. So since the algae is green, I had to use red light, as that is the light that green best absorbs. And once I obtained concentration, I can then plot that over time and obtain a growth curve. For all microorganisms, a very well-documented curve is there, where at first there's a lag phase, then an exponential growth phase, a linear increase phase, and then an exponential decay phase, which approaches the carrying capacity of the environment. Here, after a while, the nutrients in the solution or in the environment get used up, and thus the population decreases. And this is the target we're looking to get. Now, the spectrophotometer, I built this using an Arduino multicolored LED, multicolored because I wanted to make sure that the spectrophotometer worked with other colors, but I only really paid attention to the red color. Additionally, I used a photoresistor, which is a circuit element that changes its resistance according to how much incident light is cast, and a 3D printed support, which is not shown. The function, as I mentioned earlier, is to measure the absorbance and by extension, obtain the growth curve of the solution. As you can see by the image, that purple top container is a culture flask. And here I have the calibration curve of the calibration of the graph. I then pass the light through and obtain the absorbance value and pass the growth solution through it multiple times over the course of 2 weeks and compare that value with the calibration. Ultimately, I then, this is also the code for the project. And again, this may look complicated, but it's relatively simple. It just compares the voltage of the photoresistor to a known voltage and thus displays that on the Arduino's serial plotter. Now, after taking all the data and passing it through a MATLAB computation, I then received the graph you see on the left, and this is for the red LED curve. As you can see here, comparing it to the ideal growth curve, there's a small lag phase, then an exponential growth phase from 0 to 1 weeks. From 1 to 2 weeks, the growth increases exponentially, similar to that of the log curve. Had I collected data for longer, the graph would have approached the linear increase, then the exponential decay, and then the stationary phase. If I continued longer, it also approached the death phase. So what does this mean? This means that Vasudhara 1 was successful in culturing its algae. Now that we know that Vasudhara 1 works, the next question is, how does it fare to its competitor? Here is a Solaris LRO flat, which is a state-of-the-art photobioreactor used in a variety of labs. Now, comparing both the capacities, Vasudhara and the LRO flat have the same capacity. However, Vasudhara requires sunlight, which is an uncontrolled factor and is subject to change. In fact, this is one of the main reasons why the curve in the previous slide was uneven. Alternatively, the LRO flat has 4 cool white LEDs, which mimic the sunlight's wavelength and thus provide control over how much light is emitted into the solution. Vasudhara uses motorized agitation, which is still relatively inefficient. As I mentioned earlier, it is also limited by how much power the Arduino could output. Alternatively, the LRO flat uses bubbling agitation, which is a much more efficient and easier way of agitating solution. Vasudhara could only take the temperature and display the temperature, and the operator, me in this case, had to take measurements using the spectrophotometer to obtain the general cell density. Alternatively, the LRO flat can measure temperature, pH, cell density, and dissolved oxygen, as well as more factors and control for all these factors. That's why it's called a biostat, or a biologically controlled environment. However, the difference here is that the cost between Vasudhara and the LRO flat. Vasudhara only cost me about $35, and this was using the retail price of all the components. Alternatively, the Solaris LRO flat was $20,000. So if I were to make COVID vaccines, my money would be with Solaris. But if I were to teach bioengineers during a global pandemic, I would stick my money with Vasudhara. So in terms of future directions, here I have on the left the first 3D printer. In fact, it's so old that the word 3D printing didn't exist. It was called stereolithography. And on the right, I have the Creality Ender 3, one of the most accessible and versatile 3D printers on the market. And this is also the Amazon listing. At first, 3D printers took up the better part of a room, had thousands of dollars, weren't as flexible, versatile as modern 3D printers, and you probably required a PhD to operate them. Alternatively, 3D printers today have our desktop only require about $200, and they're so simple even a kid could use them. So with all this, what does it prove? Well, as time goes on, advancements in technology and improving access to these tools allow innovations to occur. So now, instead of just 3D printing toys, we can 3D print organs, and we can apply these 3D printers in a variety of other fields. I hope to see this with bioreactors one day as well, as bioreactors are a versatile technology and are useful in many applications. Thus, I'd like to conclude this presentation, and I'd like to thank Dr. William Grover for teaching and mentoring me during this, as well as the folks at UMakers for technical assistance and access to their tools. And finally, I'd like to dedicate this presentation to my grandfather, Gordon Das Bhutani, for whom my love of science and engineering has inspired me to come here to this day. Thank you.